So besides the data dependency diagrams and the fault tree analysis, we're going to talk about the Markov analysis as another tool that you can use for a quantitative system safety assessment process. In a Markov analysis, we're going to define system states. A very simple example of that would be on the bottom, where we're saying, well, the state can either be, the system can be working, or the system can be broken, or the system can fail. So we're saying, the transition, the rate at which we transition from this system functioning properly to the system being in a failed state is at the failure rate. At the same time, of course, if you're in a system state, how do I get to my system to be working properly again? Is by repairing it. So there's also a repair rate that I defined here, which we talked about really quickly earlier. So there will be transitions from a system failed state to a system functioning properly state at a rate of mu. This is a very simple Markov analysis diagram. So if you look at the data dependency diagrams that we saw before, like for example, in this particular case, a series data dependency diagram with two systems A and B, then you can also express this in terms of a Markov chain. So you can first say, well, A and B are okay, both of them are okay. So how do we transition? We can also, so first of all, we can transition from A and B both being okay to A failed. And of course, that's a final state, because if A failed, there will not be a path from the left to the right. Hence, there will not be a system. The overall system will not work anymore. So that means that if A and B are okay, A fails, that's a final terminal state for the system. And then you see that happens at a rate equivalent to the failure rate of A. At the same time, of course, you can have B failing, and that happens at a failure rate of lambda b. And then finally, you can actually say, there may be some common mode failure, if it exists at all, lambda c, that will cause both A and B to fail exactly at the same time. And of course, if that doesn't exist, you need to get rid of this branch over here. Now, if we're now going to define P sub I as the probability that I'm actually in state I, so in other words, P sub 1 is the probability I'm in state 1, P sub 2 is probability I'm in state 2, P3 that I'm in state 3, and P4 that I'm in P4, then I can actually set up a set of differential equations that represent the dynamics of this system. For example, the change in probability of being in state 1 as a function of time is really equal to the probability that you are in state 1 times the failure rates. And think about this in terms of flow. Since there is a positive failure rate from 1 to 2, that means that there is the chance that you're in state 1 is only going to decrease over time. There's no errors back to 1, so there is nothing with a plus sign. So what you're seeing is, you see that the change in the probability of being in state 1 is minus the outgoing arrow's failure rates. So it's going to be minus lambda A, minus lambda C, minus lambda B times P1. Now, so what do you do? So what about P2? So P2 actually only going to increase over time, because it will get state 1s that transition state 2 at a rate of lambda A. So that means that the derivative of P2 is going to be lambda A times P1. The amount, the probability that you're in state 1 and all the transitions from state 1 to state 2. Now, so what you're seeing is that I just defined a set of differential equations to describe the dynamics of this Markov chain. So basically, if you would give it an initial condition, for example, the system starts out in a working state, it starts out in state 1, and you use this initial condition, you could solve this set of differential equations. Very simple to realize is that this first equation is just a first order differential equation, so that means that P1 is more than likely just going to be an negative exponential. Then you can plug on P1 into these other equations and solve them very straightforwardly to get these expressions for the probabilities. So what you see indeed is that P1 is a negative exponential, so this will get smaller and smaller over time. And eventually will be zero, and that makes sense, of course, because there is no repair rate, so there's no transitions back from a failed state to the working state. So the same thing if you would do something like the parallel data dependency diagram. In this case, you see A and B are okay, so I'm on a working state. If A fails, the system still works. So you see we transition from state 1, both A and B okay, to state 2, where A is failed, at a rate of lambda sub A. Then, of course, you can actually, after that, B needs to fail, so you can actually go from 2 to 4 at lambda B. Now, in case there is a common mode error, like we saw on the previous slide right here, you would have to add also that common mode failure probability per unit of time. Yeah. So you can work out the same thing, and you can again set up a set of equations. In this case, you have to kind of look at it a little differently. Again, for one, you see you have 3 outgoing errors. So that means I'm going to have a minus sign, the sum of these 3 lambdas times P1. But for example, for P2, you see there is 1 incoming error, so that's a positive contribution, a contribution to the probability that you're in state 2 is increasing. So it means that's lambda A times P1. And of course, you still have transitions from 2 to 4, so you're going to have minus lambda B plus lambda C times 4. Think about it. If this is a water reservoir and water flows out of it, the number of water that will be in this reservoir too would decrease. And of course, the decrease depends on how much water is there to begin with. Hence, lambda B plus lambda C times P2. Yeah. Now, of course, these are very simple examples for a very simple series and parallel system. Let's look at a little bit more complicated example. So we have some sensors at the input that are being distributed to 3 processors via 2 buses. Now, furthermore, these processors then will go to the actuator. So for the Markov analysis, let's ignore the sensors and the actuators and define the processor failure rate as lambda 1 and the bus failure rate as lambda 2. Furthermore, we're going to define the state by, oh, this got screwed up a little bit, by the number of working processors x and the number of working buses y. So for example, 3,2 means that all 5 component works. 0,0 means that all of them are broken. Yeah? Okay, so let's start putting this together. So if you look at the Markov analysis for this diagram, you know, when all components are working, you're in a state 3, 2. Why? Because you have 3 working processors. Sorry, this needs to be there, remember? And 2 working buses. So 2 working buses. Now, if one of the processors, if all 3 of the processors work, each and any one of these 3 processes can fail. So there will be an outflow at a rate of 3 times lambda 1. Think about it this way. Each one of these 3 processes can fail. So if you express that in failures per unit hour, in other words, failure rate, remember failure rate is number of failures per unit time. So that means that you have 3 times the failure rate to go transition from this to this, because processor 1, 2, or 3 can fail. If in this item you only have 2 working processors, that means that only 2 can fail. Finally, if in this thing there's only 1 working process, only 1 can fail. So you see, the transition depends on the failure rate, but what you have to take into account how many working copies you have at the source of the arrow. 3 working, 2, 1. Of course, if you have 1 working processor and 1 failed, the system as a total failed, because now there's no working processors. So there's no way that the system can process the information it gets from the sensors. Yeah? At the same time, you can also have failing sensors. So in this case, 2 sensors can fail, so 2 possibilities. So you have a failure rate that's twice as big. So then at this point, if one would fail, there's only one bus that can fail. And of course, if that one fails, I'm again an overall system failure. In this case, I chose to make these two different types of failures, but really each one of those really means the system as a total fails. Now, for this one as well, you can write down the differential equations. To give an example, if you look at 2, 1, you're first going to say, okay, what are my incoming arrows? So I have 2 times lambda, 2 times the probability that I was in this state. So 2 times lambda, 2 times the probability that I was in this state. So he calls those state 1, 2, 3, 4, 5. So that means 2 would be 2, 2. So that means, yeah, so this is P2. That's, he refers that to that as P2. And you can see that in his diagram right there. So what you see is 2 lambda 2 times P2. But you also see that there's another incoming error from 3, 1. So that means that's 3 lambda 1. So that's plus 3 lambda 1 times P4, which is 3, 1. That's P4. At the same time, there's 2 outgoing errors. 1, 2, 1, 1, which is P6. I'm sorry, this is 2 times lambda 1, and of course 2 times and lambda 2. And of course these 2 arrows origin at my state 2, 1, and I have defined 2, 1 here as P5. Then again, you can take these equations and solve them in a relatively straightforward fashion. Now, what you see typically is that so far we have looked at it as a so-called continuous Markov chain. For a lot of tools, and if you want to ever do like a small problem and solve it by a tool like MATLAB or so, we would do a discrete Markov analysis. And a discrete Markov analysis again defines a set of states like 0 and 1, but in addition it defines state transition probabilities. For example, P01 defines the probability that I'm going from state 0 to state 1. So this is a probability. So the difference between the discrete Markov analysis and the continuous Markov analysis that we saw before is that in the continuous Markov analysis, this was a failure rate. It tells you something about the dynamics of the system, expressed in failures per unit of time. So for example, failures per hour. And discrete Markov analysis, we assume already a period of time and we say there's a probability. Yeah. So then you can say, okay, the probability from 1 to 0, but there's also a probability that I'm staying. So I'm thinking about the discrete Markov time is you divide the time axis into discrete epochs, and at each epoch one of these transitions can occur. So epoch 0, I can either stay in 0 or go from 0 to 1. Then the next epoch, I can stay in 0 with this probability or go to epoch 1 with P01. And in the next epoch, same thing, I'm staying with this probability in this state, and with P01, I transition to 1. Now, the initial probability, I'm going to just assume here that it's just going to be the initial probability that I'm in state 0 and the initial probability in state 1. So the way we're going to define these transitions is by means of a state transition matrix. So in the matrix, I'm defining in the row elements define from, and the column elements define the to state. So for example, the first row, first column defines the probability I'm going from state 0 to state 0. The first row, second column means from 0 to 1, etc., etc. So now if I want to calculate what my probability is at time epoch 1, I just take the probability vector at time epoch 0 and multiply it by the state transition matrix P. That's it. Think about this. You know, the new P1 element, so P01, the P01 would be the probability that you're in P0 at time epoch 0 multiplied by the transition from 0 to 0, plus the probability that you're in 1 at time epoch 0, and you transition, from 1 to 0. Okay, so what happens from time epoch 0 to 2? Well, 0 to 2, you just take P2, which is going to be equal to P1 times P, just like we saw here. The next time epoch is the previous time epoch's probability vector times the state transition matrix. So P2 is P1 times P. So what I could do though, I could take this little vector P0 times P and substitute it back for P1. So what you find out that P2 is P0 times P, or P0 times P squared. And you can actually generalize this. To go from epoch 0 to epoch n, you get Pn is equal to P0 times P to the power n. So you see, this is very simple to do. In MATLAB, you can actually take a matrix, P for example, 2 by 2 or 4 by 4 or 5 by 5 or 10 by 10, and you can take the power of that matrix to a power n. Now, another thing that you have to think about with steady state, with the Markov analysis, a discrete Markov analysis, is the steady state. You know, when we reach steady state, it means that when we have a probability vector and we propagate ahead, that the probability stays the same. Notice my probability vector, if I post multiply by p, it stays p. And this is an eigenvalue problem. And I'm not going to go into much detail how I get that, but on this slide I'm actually giving you a little bit of an example how you would have to do that. Yeah. But basically the idea is that you're going to take the transition matrix, take the transpose of it and find the eigenvectors and eigenvalues for that, and then you're going to look at which eigenvector corresponds to the one eigenvalue. You normalize the eigenvector so that the sum of the elements is 1. You take transpose, and that will give you the steady state probability row vector. So this is another example. I gave you a very simple example earlier. There's another example. Now, one thing you have to realize and do not forget is that with a continuous Markov analysis, these are failure rates. With a discrete Markov analysis, these are state transition probabilities. What you should not forget is the arrows from the state to itself. Do not forget those. Now, of course, you say, well, if I have the continuous Markov chain and then I want to go to discrete Markov chain, you can do this fairly straightforward. You're first going to define a short time interval, delta t. And if you have a continuous time Markov chain, you take the lambdas and replace them by lambda times that delta t. Think about this. When we talked about reliability, we said that the probability of failure is approximately lambda times delta t. And of course that was only valid when lambda times delta t is smaller than 0.1. So you may want to, you may want to follow the same kind of logic when picking the value for delta t. Make sure that this is definitely much smaller than 0.1. So at the same time, mu, the repair rate, post multiplied by the exposure time, the time interval. And this time interval now determines your epoch time. So if you go from epoch 0 to 1, means that delta t seconds has elapsed. Now, finally, besides these two errors, you have to add the errors that go back to the states, that go from a state to itself. Now, one thing that you have to realize is that the sum of all the outgoing errors, so the transitions away from a particular state, must be 1. Yeah, just think about it. It cannot be more than 1 because that means that the amount that magically the amount in a particular state would increase. Yeah. So in this case, it's very simple. This is an outgoing error. This is an outgoing error. 1 minus lambda delta t plus lambda delta t is 0. Yeah. So as I determined this was lambda times delta t, I know the other error needs to be 1 minus lambda delta t. It also means that the state transition matrix is given by 0, 0 to 0, 0 to 1, 1 to 0, 1 to 1. And then, if you take our previous example with the 2 buses and 3 processors, I can transition that fairly easily from continuous to discrete by post-multiplying by delta t. What I, of course, forgot in this is these arrows that go from 3, 2, to 3, 2, from 2, 2, to 2, 2, from 1, 2, back to 1, 2, etc., etc.